All right, welcome everybody. Today I want to show you and explain a little bit more slowly how a confidence interval for a single proportion works, okay? So first off, I'll say a confidence interval in general, that is where we want to know and estimate something about our entire population, but we may only have access to a sample of that population. So based off of our sample, we want to estimate something about an entire population. And that, in this case, is going to be a single proportion. So we want to know a single proportion value from our entire population. So here's our example for this specific situation. It says, out of all the students at Fargo North, we wish to know what the true proportion of students that prefer to wear sweatpants over jeans might be. Okay? So right there, that defines what our parameter is and what we are trying to estimate. That's what we want to know. We wish to know what the true proportion is. And when I say true proportion, that means out of everyone, what that actual proportion is of students that prefer to wear sweatpants over jeans. Okay. So in short, we want to know if we were to take everyone at Fargo North and poll, do they prefer sweatpants over jeans? We want to know what percent said sweatpants. Okay. Now, it's very difficult to take a census or to survey your entire population. So this is where the idea of a confidence interval comes in, where we are able to estimate what we want to know more about. So in this case, the true proportion of sweatpants people. But we can make that estimate based off of a smaller sample, okay? So here's our methodology here. It says we take a random sample of 90 students at North, and we find that 36% of them prefer sweatpants, okay? And we want to find a 95% confidence interval for the true proportion of North students who prefer wearing sweatpants over jeans, okay? So this is our task at hand. We want to find a 95% confidence interval. Well, one thing that I'll make you aware of right away is when it comes to a confidence interval for a single proportion, we have to figure out what p hat is. P hat, that is our sample proportion. So sample proportion. And it is exactly that. From our sample, we want to know what percent or what proportion qualify as a success. In other words, what percent prefer sweatpants. Well, here we're surveying 90 people, and 36 of them say that they prefer sweatpants. Now, we could keep it as 36 over 90, but if I plug that into my calculator, oftentimes we want to express that as a percentage or as a decimal. So 0.4 or 40% is our p hat value. Again, that just means out of our sample of 90 people, 40% of them prefer sweatpants, okay? So when it comes to a confidence interval, I've outlined here using our acronym of PANIC, each step along the way that we need to show in order to make this a valid confidence interval, okay? So P, that stands for defining our parameter. And this is what we want to know about our population. So what we want to estimate. Want to estimate. All right. And when it comes to a confidence interval, we never actually know what that parameter is. So in this example, we don't know what that actual proportion of all students who prefer sweatpants is. And that's what we're trying to estimate. So that's why in our parameter or our P step, we just have to write what P is equal to and what we're trying to estimate. So for our purposes, P is equal to the true proportion of F&H students who prefer sweatpants over jeans, okay? Again, we don't know what P is equal to. We just have to define what that is and show this is what we're trying to estimate, okay? So after we've defined our parameter, for our purposes, now it's just going to be P equals the true proportion. But as we get further into this, we might have to estimate what the average of something is or what the difference of two proportions might be. But here, just P equals the true proportion of students who prefer sweatpants, okay? Now, before we're able to find a confidence interval, our next step is to check some assumptions, and this will verify that the conditions for inference are met. In other words, we want to verify that we can actually use the normal curve to make a confidence interval, okay? Well, the first one, we want to know, do we have a random sample? Okay, that is always your first condition. We want to know, do we have a random sample? Okay, well, unlike an actual experiment or a survey that you're doing yourself, we can't actually know in the stem of a problem if it is random or not, unless it states that it is a random sample. Luckily for us, it says we take a random sample. So because that is stated in the problem, we're good to go on that one. It is satisfied. We can assume that it is a random sample because it is stated as such. Okay. So first condition is always to check, do we have a random sample? The second condition is that if we consider our sample size, which is n, so n is just the size of our sample. In this case, we surveyed 90 people at North High, 90 people. We want to know, is that less than 10% of all students or our entire population? Well, because at North High we have more than 900 students, that 90 is less than 10% of all students, so that is good to go as well. So in this second condition, you are comparing your sample size, here it's 90, to your population size. And we want that sample size to be less than 10% of the entire population. Okay? And the third condition, so random sample, that was stated. 10% condition, we're good to go there. The third condition is what we call the success failure condition. Okay? And what that says is in our random sample, we need to verify that we have at least 10 what we consider successes, and we have at least 10 what we consider failures. For our purposes, that means we need at least 10 people who prefer sweatpants and at least 10 people who prefer jeans instead of sweatpants, okay? Well, mathematically, the way that we check this is we take n, our sample size, times p hat. So in our purpose, or for our situation here, n is our 90 times p hat, which is 0.4. We found that up here, remember? And that is equal to 36, which is greater than 10. 10 is our magic number. That's always going to be what we're comparing to. So because 36 is greater than 10, in other words, we have 36 people who prefer sweatpants, which is more than 10, we are good to go. Now, of course, we were actually told that in the start of the problem, 36 people prefer sweatpants. So really, we didn't have to show this step. I just show you that because sometimes you are not given that 36. So that is how you would mathematically check that. Okay. And the final piece of the success failure condition is if we take n times 1 minus p hat, that is 90 times 1 minus 0.4, which is, of course, 90 times 0.6, which is 54, and that is definitely greater than 10. Okay? In other words, we have at least 10 people who do not prefer sweatpants. So because we have a random sample, because we have sample size less than 10% of our population, and because we have the success failure condition met, we're actually good to go. This verifies that we can proceed because all three of those check off, okay? Now, one quick note, if at any point you're doing a problem and you see one of these does not become satisfied, all you have to do is write proceed with caution. So here we're saying proceed, you would write proceed with caution. So for example, if we only had 8 people who prefer sweatpants and that's less than 10, we would want to make a note of that and say proceed with caution. What that tells the person reading your confidence interval is that, yes, we're going to continue making this interval, but just know that the result may or may not be reliable because one of the conditions was not met, okay? But here, all of our conditions are met, so we are good to proceed. The next thing, after we define our parameter and check our assumptions, is to name our interval, okay? So we want to know what kind of interval is this, and there are 2 ways to do this. The name of this interval is called a one proportion, because we're dealing with just one proportion, that p here, and we call it a z interval, okay? Interval, that's just because it's a confidence interval, and then the z, that comes into play here in a little bit, but that's what our critical value is. It's a z instead of a t, That doesn't mean a whole lot at this point, but that's where the z-interval comes from, okay? Another way that we can express this, instead of writing out the name, and this is what I prefer because we have to plug in numbers to a formula anyway, is just write out the formula for a one proportion z-interval. So it's p hat plus or minus z star, which I'll explain here in a moment. And then we take the square root of p hat, 1 minus p hat, over n, which is our sample size, okay? So once you've named your interval, you can either do that by stating what kind it is or writing out what that equation is for our interval. Then you want to actually find that interval, okay? So over here, before we dive into actually creating that interval, I'm going to define what each of these numbers are or each of these variables stand for so that we can just simply plug them into our interval down here, and then we can proceed from there. So let's start with p hat. Remember, p hat, that is our sample proportion, which is the percent of successes within our sample. So again, that was that out of 90 people, 36 preferred sweatpants, and 36 divided by 90 is 0.4. So that's really easy. And this 0.4 of p hat is the same thing that shows up here. And 1 minus is that same p hat here. So maybe we'll write that in. 1 minus p hat is equal to 1 minus 0.4, which is 0.6. Okay, so 1 minus p hat is 0.6, p hat is 0.4. So we've got two of our variables taken care of, p hat, 1 minus p hat. And then n, remember that is just our sample size. So n here was 90 because we sampled 90 people. And the last thing we have here is z star, okay? Now, there are a number of ways that you can find z star, but for our purposes, we're going to use technology or our calculator to find what that z star value is. And I'm going to write this out, but I'll explain what it means here in a moment. In your calculator, you're going to go to inverse norm. And the first thing you plug in is called your area. The area is going to be alpha divided by 2. Now, alpha, you don't know what that is yet, but just write it down for now. The mean is 0. Standard deviation is 1. Okay? So let me explain what that alpha means. Alpha, if we think about a confidence interval, because we have a normal curve, here at the top it says we want a 95% confidence interval. So that means the area inside our interval is 95%. When we talk about our alpha level, we are not interested in the area inside our interval, but the area outside of our interval. So if we have 95% in our interval, this little piece here and this little piece here, that's what we refer to as our alpha level. And here that would be 0.05. Okay. So for a 95% confidence interval, alpha is always 0.05, and we always divide that by 2. Okay. So if I go to my calculator, inverse norm, that is the second bars button. And if you go to option 3, it says inverse norm. This is where we're going to put our alpha divided by 2. So 0.05 divided by 2. Mean, as I said here, is 0, so nothing to change there. And standard deviation is 1, so you can keep that as it is. And just a warning to you, you can either do left or right. Left is going to give you a negative number. Right is going to give you a positive number. Either one is fine. Just take the positive of whatever shows up on your screen, okay? So here I get negative 1.959, yada, yada. I'm going to round that to 1.96, okay? So we have each of these variables defined. Let's go ahead and plug those into our formula for I, which is where we actually calculate our interval. So p hat, that's that 0.4. So let's take 0.4 plus or minus. Z star we found was 1.96. And we take that times the square root of p hat times 1 minus p hat, which is 0.4 times 0.6 divided by n, which is 90. Okay. If I simplify this, so let me go ahead and put just that piece into my calculator. 1.96 times square root of 0.4 times 0.6 divided by 90. That gives me a margin of error of 0.101. So this simplifies to 0.4 plus or minus 0.101. Okay. So to find our actual interval, this is what we refer to as our margin of error. That's just what we're adding and subtracting from p hat to find what our interval is. To find our interval, we're going to take 0.4 minus this margin of error, and that'll give us our lower bound. So let's do that. 0.4 minus 0.101 is 0.299. And then for the upper bound of our interval, we're going to take 0.4 plus 0.101, which is 0.501. Okay, so that is actually our interval. That's what our I step stands for, finding that interval. And we can interpret this as 29.9% up to 50.1%. Okay, so this is our interval. Our last step is to conclude in the context of the problem. Okay, when it comes to a conclusion here, we always want to start with our confidence level. So here, again, we're finding a 95% confidence interval. We would say we are 95% confident. So always start with your confidence level. We are 90% confident that, okay, so we have our confidence level. Then we want to refer back to what we're trying to estimate. So again, we're trying to estimate the true proportion of North students who prefer sweatpants. So we are 95% confident that the true proportion of students preferring sweatpants, so that's what we're trying to estimate. And then finally, is between 29.9% and 50.1%. So refer to our interval next. Okay. So again, when you're stating your conclusion, start with your confidence level. We are 95% confident that the true proportion of students preferring sweatpants is between 29.9% and 50.1%. Okay. So that is from top to bottom how you do a confidence interval. And again, our goal at the very start of this was to estimate something about our population. We wanted to know, out of everyone at North High, what percent prefers sweatpants. Okay. Well, because we didn't have access to the entire population, we only had a small sample of 90, we wanted to make a confidence interval to estimate what that true proportion is, okay? So after we checked our assumptions and we found that they worked out, we named our interval and found the interval. Based off of our one sample of 90 students, we are 95% confident that that true proportion is between 29.9% and 50.1%. What that means is if we took sample after sample after sample, all with 90 people in each sample, and we made a confidence interval for each of those, then 95% of those confidence intervals should contain that actual percentage, okay? So 5% of the time, we will not capture what that true proportion is, but 95% of the time, we will capture it, okay? So hopefully this helped slow things down a little bit, help you understand what it means to find a confidence interval, what our purpose is with a confidence interval, and then finally how to conclude what that confidence interval means.